Hey stat students, welcome back. Today we're going to learn about three things: the statistical problem solving process, variation in statistics, as well as misleading graphs. We're going to start right off the bat with the statistical problem solving process. There are four parts to it, okay? And we use this when we want to gather information about a population and draw conclusions, and it's the way that we go about getting that information. So the first thing that happens is we have the state process, and that's where we just have that basic ask a question of interest. What percentage of students are going to the U of M? What is the average weight of a baby cat? So on and so forth. You have a question about a population that you want answered. So my question of interest when I taught this in class last year was just what percent of my students in our class have brown hair, okay? So that's number one, the state part, ask a question of interest. Step two is the plan, okay? So that's like, how am I going to get my data? Am I going to do an observational study or am I going to do an experiment? I need data, so I need to plan what I'm going to do and what is that plan going to be, okay? And so I was just going to complete an observational study. I was going to ask students to raise their hand if they have brown hair. Now, again, this can get more complicated if you're doing an experiment, and we're going to talk all about that. You're going to learn about how to experiment the right way, but for now, we're going to keep it simple. The next part is the do, okay? This is where you get your data and you analyze your data. So I planned out how I was gonna do this. I'm gonna do an observational study. Now I'm gonna ask people to raise their hand. Yes, I have brown hair or I don't, okay? And so I do that. And so what happened in my class last year is I had 7 people who raised their hands saying they had brown hair and 16 people had other colors of hair, okay? And so I got my data right. And then when you analyze your data, oftentimes you have a graph, okay? So I did just a basic bar graph, and we're gonna have a whole unit on graphing, but the basic bar graph, many of you have seen that before, and I just went my x-axis, my y-axis, and I did it real quick as a real quick sketch. So people with brown hair right here, 30%, people with others, 70%. I should have had a label, I should have labeled the sides. But then we can really look and we can analyze that data, okay? It appears that a significant higher amount of people have other types of hair than brown in that class that I interviewed, okay? And then finally, that conclusion, and that's where you just sum it up real nicely. I always tell people, you wouldn't go to your boss and just give them that. You give them a nice conclusion about what you found. You'd interpret those results. Are they significant? Okay, so based off our study, we can conclude that about 30% of people have brown hair. This seems significant, like there's a significant difference between people with brown hair and other types of hair. Now, I shouldn't necessarily just throw out the word significant in stats. Statistically significant does have a very important meaning we're gonna learn about later, and we can actually test for that down the road, okay? Are the results significant? But right now from our eye, it looks like, hey, that's a pretty big difference. So I'm gonna call that a significant difference there. Okay, that was the 4-step statistical problem solving process. State, what's my question? Plan, how am I gonna get my data? Do, I'm gonna get and analyze my data. And finally, I'm gonna interpret those results. Are they significant? Do we have, pretty significant results there? What's happening? Pause it right now, write down any questions you have, and then I'm going to move on to the next slide. Okay, so we have variation in statistics, and you can think about that a lot. The best example I have for you with variation in statistics is flipping a coin, right? What should happen when you flip a coin 10 times? What should happen is 50% of the time you should flip tails or flip heads. That doesn't always happen, right? Okay, there's variation. You could do it 10 times one morning and you could get flat out 50%. But you could do it 10 times in the afternoon and maybe 40% of the time you flip tails, okay? There is something called variation in statistics. Okay, so sampling variability, let's write down that definition. Sampling variability means data changes from sample to sample. When I do this again in my next hour, will I get the same result? So for example, with the hair color, if I did it again for my next hour and I had people raise their hand, how many of you have brown hair? I would get different results, okay? There's sampling variability. That just happens, okay? That's normal. There's variation in statistics. There's change, okay? And now as statisticians, though, we want to ask ourselves, what is the source of that variation? the reason for that variability. Now, there's always natural variation in statistics, okay? But is there a reason we're getting different results? What are those reasons? Is it just natural variation in statistics, or has a mistake been made? Okay, so those are questions you want to be thinking in the back of your mind as you approach statistics and just as you approach, the real world as well. Why was there a change from result to result? Okay, and what was the reason for that change? All right, sources of sampling variability and sources of variation. And in case you're confused at all, guys, this stuff is just a very sliver in what we're doing for this unit. The real goal of this unit is making sure the terms you can really apply, okay? And that's what we've learned in the other one, but this is part of the big picture of when we get data, some common themes that you should know as well, okay? Different types of graphs, okay? So we're gonna actually look at misleading graphs. What should you watch out for? Okay, so I'm going to show you some things, and what I want to encourage you to do is type it out, but be writing some things down, some things to remember, okay? So misleading graphs. So I have a graph right here, and if I was in class, I would say, okay, what do you guys notice about this graph, okay? And people would say, oh, well, it's old, 1991 to 2001. We're talking about ticket prices for a baseball game versus a basketball game. They're comparing, so I would get a lot of these things happening. And then someone might raise their hand and be like, well, Mrs. Opal, or I might kind of clue you and say, well, what do you notice about the difference? It looks like there's a bigger increase, right, between basketball from 1991 to 2001 versus baseball, okay? So from $10 to $20 versus 20, well, a little bit over 20 to about 50. So a bigger increase. But here's the deal with a picture graph. This was someone's attempt to be cute and creative, which I give them credit for, right? Like that's great. However, the issue is, and let me use my mouse, so it's gonna look a little bit sloppy here because I'm using my mouse. If I did a bar graph instead, I would go like this. Now with a bar graph, right, you wanna keep the widths of your bar the same when you're doing it by hand, okay? And I'm not doing it perfect again because I'm using my trusty mouse on this smartboard app. So let's see here, and again here, right? Oh dear, that wasn't very good, but that's okay. I'm killing it, sorry guys, okay. Well, you get what I mean, you can envision it, right? Okay, now here's the issue, guys, is not only do these baseball and basketball get taller, they also get wider. So it's really misleading to the viewer. They're gonna think, whoa, basketball really, that price really increased versus baseball. It didn't increase as much, okay? And it didn't increase as much. But technically as a statistician, this is misleading to the eye, okay? The fact that it gets taller and wider. It should only get taller. The bars should stay the same width, okay? Hopefully that makes sense. What I want you to do right now is I want you to pause and write something down. Beware of the pictograph, okay? Pictures in a graph. Let's look at the next one, okay? This is again, I'd say, okay, what do you notice? Yep, it's comes from Fox News. It's from 2012, so a while ago. Looks like we're looking at GOP candidates who are running for president, okay? Or who are going to put their name in the hat for president, right? I notice there's a pie graph, and then all of a sudden, people will notice, wait, this is a pie graph, and a pie graph should be out of 100%. And if you look at this, we have 63%, 70%, 60%. Watch out for math, okay? Now, I don't doubt these numbers, but I'm guessing they took it 70% of the red group backed Palin, okay? 60% of the green group and 63% of the blue group backed Huckabee, okay? But they should be separate graphs then, okay? They should be separate graphs. A pie chart should always be out of 100. So something went wrong there. A misleading graph, watch out for it. It does happen, as you can see here. Okay, so here I have a graph, and this is a line graph, and Oftentimes with time, people do a line graph and they connect it. So they put little points and they connect it. It doesn't have to be. It's a nice way to show things over time with a line graph, but it's not a necessity. What I do want to show you though is I have 1, 2, 3 pictures. These 3 pictures are all of the exact same data. The top one, the increase appears to be, it's not that strong. The slope is pretty, flat there. It's not increasing at a fast pace from just our common eye. The same as figure 2. But figure 1 looks like that slope is a lot steeper. It's increased, the sales are increasing at a much faster rate. Well, why do all these graphs look at so different? Okay. Well, let's first look at the x-axis below. Here it goes by years. 1991, 92 by 1 year. Here it's going by 2 years. 90, 92, 94, 96. Here it's also going by 2 years. Okay, keep in mind, it's all the same data, you guys. So what's so different about these two then? If they're still going by 2-year increments, same data, why does it look so different? Well, now let's look at the y-axis. I'm gonna erase this because I have a little mark here. If you look here, it starts at 40,000, it appears, and here it starts at 10,000. Now, if you look, it starts at 10,000, then it goes by another 10,000, and it keeps increasing at a rate of $10,000 or $10,000 in millions. Okay, so keeps increasing at that same rate. But here it starts at, 40,000, and then it increases by 5,000 only, okay? Here's the issue. Whatever that first tick mark is, that's your scale, okay? Otherwise, it's considered misleading. So I started at 10,000. That's okay to start at, but then the next number has to go by 10,000 as well. So 10,000 plus 10,000 is 20,000. That's okay. 20,000 plus 10,000 is 30,000, so on and so forth. Same thing here. The scale is just fine. It's increasing by 10,000 each time. But the issue is here, it starts at 40,000, so the next one should be 80,000, and then 120,000, and then 160,000. The first mark is what your scale should be. Otherwise, it's considered misleading. So this one right here is misleading because of the scale. Now, if it was me and I'm at home watching this video and I'm taking diligent notes, what I would pause and I would say another misleading graph is to watch out for scales, okay? Because you can mislead people with statistics if the scales are off. And a true statistician does not want to mislead people with their data. All right, you guys, that's it for today. So what should we have learned today? We should have learned about misleading graphs, what to watch out for scales, make sure the math is done correctly. It comes out of 100 if it's a pie chart. Make sure that we don't have a pictograph. We talked about variation, there's change, and why is there change? And then finally, we talked about the 4 steps in statistical problem solving. State, plan, do, conclude. Okay, you're gonna get back with your teacher, so make sure you write down any questions you have and bring those to the teacher. And we will see you guys again soon. Take care.